Right now, officially, hello everyone. So yeah, today I want to give you a presentation update about my current work on the SDR subsystem of OPSAT. It is my last day of the internship, and I would like to give you some pointers and explain what I did and how it can become useful and in the future operational use. In this presentation, I wanted to cover the purpose of my experiment, the background, how I imagine it to be, the current SDR subsystem, outline how it used to work before any of the changes have been made, and then explain to you my take on the new operational use of the SDR. How I imagined the new operational use to be, and what tools I implemented to help with this. I also cover the the differences between the two approaches in terms of memory savings, and I'll give you some ideas how we can schedule it and deploy it operationally. And then I will cover any future improvements we can make to make it even work even better. But maybe not for this mission, but maybe for any of the future missions. Starting first, the purpose of the experiment is as follows. So far, we've seen that the SDR recordings are large in size, and the current constraint is the memory of the experimental computer. So when I joined the internship, the longest recording we could do was constrained by 16 megabytes, and that was between 2 and 10 seconds, depending on the sample rate we were using for the recordings. That was very much constrained. Then the people from Seedlock experiment from Libre Space Foundation introduced streaming experiment 202, but it still was constrained by the memory of the experimental computer because it was streaming to the computer, and the computer was saving the samples into its own effectively into RAM memory because we use overlay file system. So the goal of my experiment is, first of all, introduce recording straight to the eMMC to bypass the constraint of the RAM of this experimental computer, just enabling longer recordings. We can go further than the amount of RAM we have, and it's only constrained by the available partition size on the eMMC. The second goal, if we assume that we can do longer recordings, we need some tools to deal with those longer recordings. As I said, SDR recordings generate a lot of data. So a minute recording is already 200 megabytes, and this is not viable to downlink using our current methods. Like 200 megabyte file would probably take over a week to downlink. So then we need some tools to sort of chop up the samples in an effective manner so they can be quickly downlinked to Earth. And goal 3, I thought that it's sort of a summary of my experiences so far with the internship. So I wanted to apply as much operational knowledge I gained working with other experiments and working with the daily operations to make the experiment more or less good to use, not too hard, and hopefully much more clearer than other options. Background is this is a recording I did in Hamburg in December, and me and my friends, we stood with antenna pointed at an OPSAT, and we did the original the recording in the original Seedlock configuration. So we were recording into the so Rodrigo scheduled the recording on board OPSAT. We were trying to transmit a message, and the current version back then of Seedlock I was recording to the RAM memory. So the entire recording is constrained to just 30 seconds. Well, just or maybe it's 30 seconds. It's quite long, yeah. So, but maybe it could go longer, yeah. First of all is that. But then once we recorded this sample, it took us about 2 weeks to download it. First week was just various problems with OPSAT, and we needed to stabilize it and get it into the right configuration. And then once we started downlinking, it took like I believe 2-3 days to downlink the entire 100 megabyte recording. But in the end, what I really wanted from this entire recording is this one simple transmission in the middle, which was the one we transmitted. And once I downlinked it and separated it, it turns out that this conversation itself is like just few megabytes. So if we develop some tools, we could downlink it maybe within a day. If we had some tool to extract it on board the satellite and then downlink forever. So yeah, this is the idea. And here I wanted to highlight some of the previous, how the previous system works, just on a graph, and how the new system would work. So as I've already explained, we have the SDR system, subsystem, and it goes through the FPGA. It streams the samples thanks to FPGA firmware to the SEP, to the experimental computer, and on the experimental computer it is processed by a special binary. But the binary so far, as it was developed in the experiment 202, it was saving directly to the SEP file system. And only after the recording has finished, we could store it to the eMMC and persist it between reboots. But we did not gain anything in terms of the extra eMMC memory. Yeah, we were still constrained by the SEP file system. So effectively, the recordings were limited to about 100 megabytes. And more than 100 megabytes, we would be risking a reboot of the SEP or maybe influencing some other experiments that are going on board. And then sort of the first batch I imagined was using waterfall software to at least get the idea of what we have recorded and generate a similar image to this. This is a waterfall image already on board. So at least we have some additional information, what has been recorded, and is it even worth downlinking? But at this stage, it was still binary. It was like, yeah, we have a recording, or yeah, we don't have a recording. Yeah, so we did not have any tools to manage the recording on board. So this comes to the idea of sort of version 2.0 of this setup. And it's modifying the binary from SIDLOG to allow it to download, to record straight to the eMMC, which turned out to be quite easy because it's in Linux file system, and any device connected to it is just a file, and we can write to that file in binary. So yeah, in our case, the eMMC is attached as a partition, but due to the constraints, honestly, I don't really understand, nor I want to get into. We cannot really mount this and use the file system of the partition. So we have to do binary writes to it. So yeah, this thing I can say that was already done, and I will cover it in the next slides. And then once we figure out this problem, the next problem is to build the tooling around it to effectively extract the data out of it. And first of it is again the waterfall, but this time it takes the data from the eMMC directly, and this way we can preview what we have recorded. And it can be even a longer recording, longer than 100, 200 megabytes. Maybe in the future we could go a little bit higher. And with such a long recording, we can generate a waterfall, which is fraction of the original size of the samples. And then we can downlink, or rather, yeah, first generate the waterfall of a smaller size to the SEP file system, and then effectively downlink it to Earth to get a good preview of what we have recorded. And once we have the waterfall on ground, we can make a decision on what to downlink. And then either via schedule or via Automax, we can input parameters to another sort of program on board, which will cut the recording from the eMMC memory into manageable chunks. So yeah, this is more or less the outline of how I imagined the new system to work. And yeah, it leads us to the new operational sort of procedure I tried to implement. So yeah, just to summarize, the current procedure would be make a wideband recording. By widebands, I mean the current original setting of the SDR. So for example, 1.5 megahertz bandwidth recording, which gives us an overview over 1.5 megahertz of frequencies around the center frequency we want to record. So in this case, yeah, we have a middle frequency here, and it covers 750 kilohertz to the left and 750 kilohertz to the right. But we can even go higher. The highest setting on the SDR can go up to 20 megahertz bandwidth. So in either case, we can make this wide range recording just to see what types of signals are in the range, and then we just downlink the waterfall. So we can, like, for now we just ignore the recording, we downlink the waterfall. And this is the actual waterfall generated on board of the satellite. And then we can find interesting signals. So in my case, yeah, I have a window here, and I can just select it, and I can find what frequency it is within the spectrogram, within the waterfall. And then I can input this data back to the satellite for downsampling. The satellite will return a file which only includes this signal, and then I can downlink just this signal. So below you have a screenshot of a recording already on ground, and instead of the wideband, you have just a signal in about 20 kilohertz range. So in sorry, I don't hear you. Sorry.
Okay, now can you go one slide back?
Yeah.
Do you already know how much reduction in downlink data bandwidth we get from this?
Yeah, I will cover it in the next slide, in one of the last slides.
Okay, thanks.
Yeah, so so in order to implement this procedure, my experiment supports sort of what I call actions. So it's one experiment, but it has 4 distinctive tasks or actions it can do. So the first 2 core functionalities are the record and waterfall actions. And the record one is very much as it used to be before. I even use the same parameter names in order not to introduce any more confusion in how the SDR system works. So whatever knowledge you have about the SDR from before, I did not want to touch it, so everything still applies. Yeah, so you do the standard thing of selecting the center carrier frequency. Then you have to select the frequency index and the low pass. Actually, I will cover it in the next slide. It's not so important now, but yeah, 4 actions. And 2 of the actions are record and waterfall. So the first step of doing recording on board is scheduling the record action. Then the record action will do the recording, of course, with the given parameters. And then it's also connected. If you set waterfall render to true, it will also trigger the next action, which is waterfall. This is like the core functionality. The recording will be done into the eMMC, and it will be never seen on the SEP recording, on the SEP file system. So you need to get the waterfall, and this is the only sort of proof of the presence of the recording in the SEP file system. And then this waterfall, alongside with the log from this operation, can be downlinked to Earth, and then we can proceed with the rest of the procedure. But despite that, the waterfall is still a separate procedure. So for example, if you experience a reboot, or in any other way you delete the waterfall, then you can just trigger this part of the procedure, and it will automatically pull the recording from the eMMC. It will stream out the recording out of the eMMC, and it will generate another waterfall for you. So yeah, you don't have to do the recording again to just get the waterfall. And then the third action is the downsampling function. It accepts parameters to select the given signal, and then it also, without extracting the full recording, it will stream it out of the memory. It will apply the parameters, which I will explain in the next slide, and you will be left with a small file only of the signal. So in those 3 procedures, at any given moment, the recording is always starting the eMMC, so it's invisible from the SEP memory. It doesn't really matter how long it is, because you only downlink the waterfall, and then you can also just downlink the downsampled part of the signal. So that the new constraint at this point is this maximum size of the signal you downsample, and the maximum size of the waterfall, but we can cover it later. And the for action is sort of legacy one, but it's kind of unsafe to use, and it is the actual procedure to downlink it from the eMMC. But currently, the experiment is sort of calibrated to use 200 megabytes of the eMMC memory. So I'm pretty sure if we run it on empty SEP, we could actually downlink everything from the memory. But yeah, in the other case, we risk reboot of the system. So it is implemented. You can do it, but you probably should never use it. Maybe for debug on the EM, but on the flight model, it should probably be never used. Yeah, and in all sort of actions, you can also always downlink the log and the output, so waterfall or the downsample signal, using another command. Yeah, so you can either use Automax or experiment 1003 to extract the results operationally, or you can just set this flag in the experiment, and it will automatically downlink to the specified downlink path in the config. So the experiment can be sort of autonomous from the operational perspective. So yeah, now I actually want to cover the particular sort of parameters for all the actions. And I wanted to start with the SDR recording parameters. Yeah? So just some background on what we have so far. So yeah, the carrier frequency is the center frequency you actually tune the SDR2. So as you could imagine, I have like a helper spectrum down there. This is like the entire radio spectrum. Excuse me. This is like the entire radio spectrum, and then you can select, okay, I wanna listen to this frequency, for example, here. And then, okay, the SEP only supports frequencies from 300 megahertz to 3 gigahertz, and in this range you can select this value. And then the next value you need to select is the sampling frequency index. And the available indexes are listed here. So it goes from 1.5 megahertz up to 80 megahertz. And it basically specifies you the bandwidth of the recording that's going to be performed. So around the center frequency, how many megahertz there will be of bandwidth. Effectively, it means that for a 1.5 megahertz bandwidth, so index 0 in this case, you will have 750 kilohertz to the right and 750 kilohertz to the left, altogether 1.5 megahertz. But we can go up to 80 megahertz, which would be theoretically 40 megahertz to the left and 40 megahertz to the right. But effectively, it also means that we don't have enough memory to do long enough recording at such a sampling rate, but perhaps I will go to it in the next step. Another parameter we need to set is the low pass filter bandwidth configuration. This is kind of funny because the numbers are reversed, but you need to match it with the above values. So for 1.5 megahertz, you want to do 0.75 kilohertz filter, and this is because if you set the sample rate to 1.5 megahertz, as I said, you have 750 kilohertz to the left and to the right, but then you want to filter out everything that is outside of this range. Otherwise, everything will overlap, and you will hear everything at the same time in the same range. So this is called aliasing. So in order for that not to happen, you need to set the filter to a value which is, well, in this case, half of it. So the low-pass filter will filter everything above 750 kilohertz and below, but it's kind of mirrored. So yeah, it will cover the same range as the 1.5 megahertz bandwidth. Yeah, I just noticed that the specified list of the low-pass filters covers everything up to 14 megahertz, so it doesn't exactly cover all the sampling frequency range, but it's very likely we're not going to use any of the higher frequencies. The first setting is the gain. I actually have not made extensive tests with different values. I believe this is the software gain, which will be applied to the sample, so it will allow you to sort of set the dynamic of the signal, how the signals are sort of amplified on top of the noise floor of the recording. I have not made many tests with that. I use 60 decibels with great results. But if you're looking for any particular signal which is quite quite low, quite not powerful enough, then you can try boosting to 72 decibels. I had great success with 60 decibels so far. Another setting from the SDR side is calibrate frontend. And the official documentation says that it should be used every time we change the low pass config parameter. If you do not trigger the calibrate frontend but change the low pass filter setting, you will get an error message. Well, you get a warning message. But honestly, I tried it with and without, and I didn't see much difference. So it's probably good to do it, but yeah, generally I did not see much difference between the recordings. And the third and actually the last setting I wanted to cover is the number of samples. And in the current version of the experiment, you don't really need to change this parameter because I have calibrated it to the current size of the partition. So before it used to be 25 million samples to achieve 100 megabyte recording into the set memory, but now the partition is almost 200 megabytes, around 190 megabytes, and I calibrated it to 48 million, which in turn corresponds to about a minute of the recording. So you don't really need to touch it, but I just wanted to cover that the size of the recording is basically the number of samples times 4 bytes, because each sample consists of 4 bytes. 2 bytes for a 16-bit short number for the I sample, and 16 bits short value for the Q sample. Or rather, both of those numbers are one sample. Yeah, so 32 bits, 4 bytes, 32 bits, 16 bits per number in one sample. So yeah, now I wanted to cover the sort of how the files are stored in the eMMC. So far, yeah, I covered they are kind of invisible from the set memory, but I wanted to implement it in such a way that it will work with any of the currently used operational procedures and with already present sort of operational knowledge you might have from working with other experiments. And I found it would be the easiest to implement the tar format as a format to store the samples. So if I just wrote the binary samples to the eMMC memory, then I would have a bit of trouble with sort of extracting those values, because the IQ samples are just number, as I covered. Yeah, it's 16 bits of one number, 16 bits of another number, and the software to sort of process those samples, it doesn't recognize if it's just a 0. Instead of an actual sample, it will think it is a sample. So there is no sort of bounds in which we can contain the sample, the recording by default. So I needed to have some sort of a simple format to contain it, and turns out tar is fine. So I added modification to the SIDLOG experiment to write a tar header and before it starts the recording. Then it writes a tar file name header with a file name, including all of the metadata of the recording. It also knows the length of the recording beforehand, because we specified the 48 million samples as the length. So it allocates the space for the recording. It does the recording into the memory space on the partition, and then it writes a footer, tar footer, file name footer, and then closes off the tar sort of file with another footer. So then in those bounds, I can use standard tar commands to extract a given file name. In this case, I can just extract the samples, and as an added bonus, I have the metadata stored in the file name. Yeah, it's nice. Perhaps there could be like another text file at the end of it. It's quite extensible. I think in the next version I will need to add the log file at the end. But in either case, it's quite extensible. You can modify it. You can add something in front or in the back, and you can work with it using currently used tools. But yeah, I guess the metadata could be saved in a text file, but this works fine. So 10 out of 10, best solution. So then now I wanted to cover the next part, the next action of my experiment, which is waterfall. So yeah, we did the recording. By default, after the recording, the waterfall will also be generated, but you can also trigger the waterfall manually. So I just wanted to cover the 3 parameters which go into this waterfall procedure. And first is the windowing function. Honestly, I don't know how to explain it the best. Like the sort of the way to explain it easiest for me, when I try the different windows, it sort of gives you a different contrast of the actual image. Of course, it has a different use from the perspective of the signal, but the easiest way to explain it is that the different windows have a different way to sort of aggregate the frequencies, and in the end, from the perspective of the picture, they give you a little bit different contrast of what is a noise and what is a signal, how powerful is the signal. But in my current testing, I used the Blackman-Harris window. It seemed to perform the best and give the best results. So I just left it as the to be default to Blackman-Harris. But if you have any other idea or you want to play around with it, these are all the available windowing functions for the waterfall software. Then next one, perhaps more important one, is sort of the initial width of the waterfall, and you can pick a number which goes in the square of 2. So low number means that the initial waterfall will be narrow. And in this case, it means that each pixel is sort of one frequency in the recording. Yeah. So if we made 1.5 megahertz bandwidth recording, but we use only 2048 windows, waterfall size. This stands for fast Fourier transform. I just realized. Then all of the 1.5 million frequencies will be sort of squeezed into 248 sort of buckets. 1 pixel is 1 frequency. So I don't know exactly how many frequencies one pixel will contain, but it will be several frequencies. So instead, you probably want to go for a higher number. I use 6,384 for 1.5 megahertz recordings, and it gives you a sweet spot. The waterfall is a bit wider, and you can see all the signals in the spectrum. They're actually not here, but so you can see all the different signals and you can distinguish between them, and you can see it better. One thing to note, it doesn't change the actual size of the waterfall. It will change the proportions of the waterfall. So those both images will still weigh the same, about 8 megabytes for 100 megabytes recording, but you will have either temporal resolution in time, or you will have frequency resolution in the frequency domain. So this is sort of something to pay attention. And then speaking of size, there is also a flag to convert the waterfall to JPEG. I leave it on by default, but maybe you want to turn it off. The PNG weighs about 20 megabytes for 100 megabytes recording. And the JPEG weighs about another half of that, about 8 to 10 megabytes. I must note that the size of the JPEG is also sort of, it is defined by how many signal, how many noise we have. So it might not be always the same. It's usually when there is white noise, it weighs what I said. But if there was no white noise, it would weigh much less. Yeah? For reference, I give you the link to the GitHub page. It's actually a fork made by Tom from another program. But yeah, here is a bit more documentation about it. Yeah, so now let's talk about the downsampling. So as I already covered, you have the waterfall, which will get generated on board of the spacecraft, and you will downlink it. And then at this stage of the presentation, I thought, yeah, it would take me probably several slides to just explain to you how exactly to calculate those parameters for downsampling. And then I decided to just write a quick Python program to do it for you. I mean, you can still sort of understand how the program works. It's just 5 quite easy sort of mathematical procedures, but I just made the effort to calibrate it and test it myself, and then the program is reasonably accurate with what we want to accomplish. Plus, it goes into the direction of providing the mission control team a tool to use and maybe perhaps spend their time on something more important than calculating math stuff. So yeah, the idea is you load the waterfall picture into the program. You can select on a given frequency. In my case, I already know what I want to downlink, but in your case, you would probably need to do several tries. So select a signal, get the parameters, downlink it, see if it's the signal you look for, and then adjust. But in my case, it's this. So you just, okay, of course, you load the waterfall. You need to first input the sample rate of the recording. By default, I set it to 1.5 megahertz. But yeah, set it to the actual recording time, actual recording sample rate there is it was on the spacecraft, because it will define the width of the image. Yeah. So as I said, the sample rate directly corresponds with the bandwidth, and the bandwidth will be 750 kilohertz in both directions. And then based on this, you can select the square, and the position of the square will be calculated in hertz. Yeah. So it's not a sort of pixel coordinate, but it is the coordinate in the frequency domain. And the program will automatically calculate for you two parameters. First one is downsampling shift, which basically means how far from the center the middle of the signal is. And then another one is frequency, cutoff frequency, downsampling cutoff frequency, which defines sort of the width of the signal and the new sample rate we're going to apply. So then I want to explain to you the logic of the entire procedure. How do we use then the two parameters? And the general idea is that we have the entire recording on board, saved in the eMMC memory. And then we select the frequency we want to downlink and shift it by this amount to the middle of the spectrum. So this is where the shift frequency comes from. It's the on one side, it is the sort of position of the signal from the center, but then we do the opposite. So we subtract this frequency from the recording, and we effectively move the recording to the middle. And once it is in the middle, we do the actual resampling of the signal. So there are two parts to it, which you don't really need to understand. But first one, as I explained with the recording step, first procedure applies a low-pass filter. So it filters out everything which is outside of this range. This is what's called a cutoff frequency, because this will be the maximum frequency which is kept. Everything else will be rejected outside of that. And so once you only have the signal in this sort of box, then you can effectively resample it. So you pick there is a decimation rate calculated, and for example, every 10th sample is being saved. So here you can see where the memory savings come from. The decimation, the downsampling procedure, it actually keeps only 10th, for example, 10th sample based on the new sort of cutoff frequency we specified. So instead of keeping 1.5 million samples, it will keep 20,000 samples, for example. Yeah. Or rather, instead of 25 million samples, it will keep every 10th, which will be 2.5 million samples. And there you would see a tenfold improvement in the file size. So yeah. Once you have those parameters from the program before, you can go back to the configuration of my experiment. You can select the action downsample, and then you input those two parameters into the experiment: the downsample shift, which is the sort of the position from the middle, and then sample cutoff frequency, which is sort of going to be the new it's not going to be the new sample rate, but it's going to be the new the frequency at which we will cut off. And again, I also added two helper commands to generate additional waterfall just for good measure, just so you can get a quick feedback on what you're doing. And in this case, if you decide to do the waterfall, again, you probably need to adjust the FFT size. There is an additional parameter to do it. Here, I keep it a much lower value just because we are dealing with much smaller bandwidth. You can have a quick preview of what you have just cut out. And in this case, the waterfall will wait literally just few kilobytes. So it will downlink right away. Just like you could probably do it via Automax, and you would get the results live during a pass. So I think it's a really nice addition to it. Yeah. So just to cover a bit about how the procedure works, it will read the parameters of the recording, the metadata of the recording, which is stored already in the eMMC. It will read the center frequency from the file. It will read the sampling frequency from the file name. and it will calculate, it will apply those parameters to the metadata. Yeah, so it'll actually give you feedback. What's gonna be the new middle frequency? What is gonna be and what is gonna be the new sampling rate of the signal? And this new metadata will be also saved in the output file name of the downsample signal. Yeah, one thing to note: the original recording had 1.5 megahertz sampling rate. Then you decide on your own cutoff frequency, and then from this cutoff frequency, there is a new sampling rate generated. So it's going to be rounded up to the nearest natural value of the sort of cutoff frequency. Yeah, so effectively you need to use this value from now on to replay the signal. Yeah, and this is how it looks from the ground state once the file downlinks. As I mentioned here, right now to open this recording, you need to input the new value for sample rate, and then the recording will open. You cannot use the previous value of 1.5 megahertz. Well, you can, but the recording will not be played in real time. It will be played in a quicker time than real time. In my case, I use the software SDR Sharp, and I just wanted to cover quickly how you can open such a file after downloading. You can go to the menu, burger menu over here, go to source, baseband file player. Then you load the file. It asks you for the parameters, and you need to, as I said, input the new sample rate specified in the file name. And the format, it's 16 bits per sample and one channel of the recording. And also, if you see that the program crashes or maybe it will freeze, then you also need to the menu display resolution. It's usually open here as a window, and try to lower the resolution which is below the current bandwidth. So it's the same command from waterfall FFT size applies. This is the same parameter, but in a different software. So yeah, effectively, this is the one signal I wanted to downlink, and now I believe we can cover the memory savings. So yeah, I have two scenarios outlined here, which I have tested extensively, and this is the previous 100 megabytes recordings to the eMMC. And at 1.5 megahertz megasamples per second sampling time, sampling frequency, we could do 33 seconds of the recording, and it fit in about 100 megabytes. So yeah, or 25 million samples. Then out of the signal, I generate a waterfall in PNG format, and this is 20 megabytes, so a fifth of the original size. But then, yeah, we can still compress it to a JPEG, and then it is about 8 megabytes. Thing of note, those files will exist for a brief moment in parallel of the file in the file system. So it will be 28 megabytes for a second. Then the file will be the PNG file will be deleted, and you are left with an 8 megabyte file. And then the performance for the downsampling is, from my experience, as follows. So if I cut out a signal of 100 kilohertz bandwidth, I got a 6 megabytes file. And if I downsampled to 25 kilohertz, which is about the size of the recording here, it was 2 megabytes. So as you can see, this is a simple voice transmission I made with my own radio, and I believe the original bandwidth of my radio is like 10 kilohertz. And then I just downlinked a little bit more around that to account for the Doppler shift, because the signal is a bit skewed. And the final file size is 25 kilohertz. Yeah, this was the 100 megabyte recording. And in the new configuration, which has been tested on the EM but has not yet been deployed on the FM, I bumped the original file size to 119 megabytes, which corresponds to about a minute at the same sample rate. Of course, if you give it a higher sample rate, the recording time will get lower. But still, yeah, you have more room to play around with. And in this configuration, the original waterfall PNG is 40 megabytes. and then the JPEG compressed from that is about 15 megabytes. So it's again a bit bigger file, but I believe we should be able to downlink this file in like what, about 3 to 4 passes, I think, if we get good signal. So it's still better than waiting 2 or 3 days for the entire 190 megabytes to downlink. Yeah. And once the JPEG downloads, you can, of course, make the decision. And the downsampling signals are basically doubled just because of the extra sort of time. Extra, there are more samples, so the file is about twice as big. So it's 12 and 4 megabytes. Yeah. So this is the outline of the memory savings. One thing to note that the current constraint, as it is right now, is the PNG size. So if we doubled the original file size again, and the PNG file size was about 80 megabytes, if we doubled it again and it was like about 120 megabytes, then we would go into some trouble, yeah, because the PNG. So we could go up to about 4 minutes of recording time by expanding the partition, the eMMC partition, but then we'll run in another constraint, which is the temporary size of the PNG file which is generated. I wanted to fix it, but by recompiling the waterfall binary and introduce a change which would allow me to stream the data instead of just saving it to the to the SEP file system. This would allow us to just go straight to the JPEG, do the compression right away, and never create this temporary file. But so far, I was unable to. There is the SEP build Docker container. I couldn't figure out how exactly to install dependencies on it and how to fix this issue. But for now, it's not an issue yet. But it might be an issue if we decide to make the original original recording a little bit bigger. But regardless, I'll try to work on it in the future. So yeah, I just wanted to cover quickly how would you schedule it, and there are two approaches we discussed. So in the so the entire experiment was made with new firmware in mind. The experiment 223 firmware in essence should combine all of the required FPGA firmwares for operational use. So that would be the SIDLock FPGA firmware allowing streaming of the samples from the SDR subsystem, but also the SpaceWire, the FPGA core required for SpaceWire communication, and effectively also the Automax communication, or overall the communication with the SEP over SSH and IP packets. So this is in such case, if we would have on board of the flight model the experiment 223 firmware loaded, then we can do anything without any reboots. So you just call my experiment with the right parameters. I have prepared the templates in our scheduling document, and you can just schedule one of those 3 actions via schedule. So there is the record action, the downsample action, and the waterfall action. And I already pre-made some of the set commands used to change the configs on the fly. Or you can also, of course, change the config via Automax, depending on what fits your operational use. Yeah, the thing to note: everything is configured by the configuration file. So yeah, it should be quite easy. But then if the firmware 223 is not loaded, then we can work with the experiment 202 firmware, which is just the FPGA firmware, but then it requires to reboot into this image and reboot out of this image. So one thing to note, I have not actually made the new template for it, but in essence, it should use the same template from experiment 202. You just need to make sure that my experiment is installed. So it would need to be put into the some of the eMMC partitions. It needs to get extracted, and then the record action which would need to be run, and then the record action, it by default saves the samples to the eMMC memory. But as it stands right now, it will not save the log file. So the log file, you either need to save yourself manually, or in the next version, I will add a functionality that it will be saved to the eMMC memory after the recording in the same memory space. But so yeah, this is the caveat currently. And yeah, then you would reboot out of the experiment 202 firmware into the normal standard firmware with the IP functionality, and then you could process the rest using Automax and the standard operational tools. Yeah, so this is from the perspective of the planning, and I just wanted to give you a background about how I sort of laid out the experiment. So the entry point to the experiment is the standard start command used by all of the experiments. But then I sort of mixed it up by having the config file, which defines the behavior of the experiment. So effectively, inside I have 3 plus some helper functions. I have 3 programs and then some helper functions. And basically the action corresponds to which sub procedure will be run. So if you select action record, then there is a program record. If there is action downsample, there is a separate program called downsample, and action waterfall is another program called waterfall, which sort of are hidden behind this single command. Which also means that in testing and development and whatever, you can call these commands directly. You can also call these commands directly, for example, via Automax, and they will read the config file, and they will actually do the same functionality as starting it from the original command. Yeah. And then, yeah, there is also some of the downlink helper commands, of which I explicitly specify the downlink action, which we'll call the helper function. But I also have some other helper function you can see in the source code of the app. So there is like pick EMMC function, for example, which will open the partition for you and print what file is stored inside. So it will print the file name of the recording inside. Or you can, for example, call the helper function EMMC metadata, and it will do the same, but then it will parse the file name of the recording, and it will print you the data exactly like this. Yeah, so it will tell you the center frequency, sampling rate, low pass filter gain, everything read from the file name. Yeah, so you can get some situation awareness example. For example, after a reboot, you can just pick and remember what was recorded, what was the last recording which is stored, or maybe you can see that there is no recording stored on board. And yeah, also, as I mentioned, the commands can be called directly. They will read the config file on their own, and they will run separately. So yeah, this is basically the outline of the experiment, and I have some next steps written down. Namely, for example, I have not used fabric compression for the waterfall images. This is definitely a low-hanging fruit which could be added. The waterfall JPEG, which is currently 8 to 16 megabytes, could be compressed furthermore using lossless compression. That would be something to test. Should be quite easy to implement. What I have not implemented is splitting the samples in the time domain. By time domain, I mean that when you select the square in the program, I only take into the account sort of the horizontal parameters, so the frequency parameters, where the signal is located, but I'm not taking into account the parameters on the vertical axis. So next improvement would be to add when the signal starts and when the signal stops. So for example, in the case of this signal, I could just ignore all the samples before and all the samples after. And this would introduce even more memory savings. Whoops. Another future steps to take, larger partition, of course, we could extend the overall recording time. For now, I also accept only one downsampling at a time. So if you want to extract more than one signal, you need to schedule several downsampling actions in the schedule or in Automax. Another point, I wrote everything in Bash because it was the easiest to do. It was really easy for prototyping, but if we want to add more functionalities, for example, like the ones above, I should probably use Python. Python is a little bit better with math. So far, I did not have to do much math. I was just passing parameters between the different programs. So I didn't really need to do any complicated operations in my program. But yeah, probably it would be wise to start over with Python and add some more functionalities. But it works fine so far. So yeah, it's something for the future. Another thing is to sort of flip the project on its head. So instead of doing the sampling, the downsampling after the recording, we can do it at the moment of recording. So it effectively would mean that we would never be saving samples which are outside of the specified range. And but this is a bit tricky because we would need to know beforehand exactly where the signal is going to be in the radio spectrum, including the Doppler shift and any other shifts there might be. But yeah, this could also be done perhaps. And then last thing I'm thinking, this is actually what Tom did originally with his experiment, and I think it's obvious from how the experiment works so far. It begs to introduce some sort of an AI signal detection, so we don't even need to download the waterfall in the first place and sort of apply an operational knowledge on ground. There could be a pre-trained AI model which would detect effectively all signals like these, yeah, and it could generate the parameters on board and autonomously sort of maybe rank them in order based on how powerful they are. So, for example, it would downlink these signals first, and then it would downlink all the rest of the signals, but ignore everything else in between. So yeah, this is sort of the things I could think of which could be improved for the next part. And for me, it's a bit of a shame that I got this late into my internship to develop this. Although also it's a bit of a shame we got to work on the SDR this late into the mission, because if the mission flew a little bit longer, we could basically have what is effectively SmartCam for SDR recordings, I believe. And we could have a lot of fun with it over the next coming months. But yeah, currently the date for the orbiting of Opis is like May. So yeah, hopefully you can make the most out of it in this period. But yeah, otherwise I think it's really good. So I just want to give a summary and a comments based on sort of the context of the master thesis. And sort of I realized while doing this experiment that the technical implementation I came up with is nothing complicated. It is not sort of a state-of-the-art implementation which tries to revolutionize anything. It was quite easy. I used a few blocks I found from open source repositories. I used some of the methods already developed by Tom at the beginning of the mission, but it was rather an exercise in organizing all the different tools and routines and programs we have or have been developed at different points in the OPSAT lifetime, and sort of put it into one sort of package which serves a purpose and is perhaps better documented. So in the context of my master thesis, this entire sort of journey is not so much about the radio and the technical implementation, but about all of my experiences with operating a satellite and the different things I needed to pay attention to. And yeah, how does it look in real life? And realistically, the output of this experiment is the entire operational loop which I try to describe to you and which I hope will be useful in the coming operational use for in the end of the OPSAT mission. So yeah, this is basically it. I just wanted to highlight some contact details. As I've mentioned, I'm finishing the internship today. So yeah, if you have any questions, let's stay in touch. Here you can see some of my contact information, and hopefully this experiment will be useful in the coming months. And yeah, also on top of that, I should be available on the Teams channel for the SDR subsystem. So yeah, if anybody in the future has any questions, then I should be available to support. So with that said, thank you for the presentation, and I can accept questions.